the equation for the torque that is needed to raise a load, and that was TR equals to the weight of the load that we want to raise, or F, multiplied by the mean diameter divided by 2, multiplied by the lead, plus the friction multiplied by pi mean diameter divided by pi the mean diameter minus the friction coefficient times the lead. And this is equation 8.1 in your textbook. So this is the TR, is the torque required to raise a load that has a weight F, or is applying a force F on the power screw. Another expression for the torque required to lower the load, TL, we had F dm divided by 2 multiplied by pi friction coefficient mean diameter minus the lead, L, divided by pi dm plus the friction coefficients times the lead, L. And this is equation 8.2 in your textbook, where TL is the torque required to lower a load that is exerting a force F. We also looked at the self-locking condition to prevent the load from turning the power screw, and that was that the friction coefficient must be greater than 10 lambda. We also looked at power screw efficiency. Where we had the efficiency E is equal to T naught divided by TR, where T naught is equal to FL divided by 2 pi. Basically, the torque required when the friction is equal to 0. If instead of using square threads, if Acme threads are used, instead of square threads, the thread angle creates a wedging action. So this will require a greater torque. So the raising torque will become equal to F dm over 2 multiplied by L plus pi F dm multiplied by secant alpha divided by pi dm minus FL secant alpha, where 2 alpha is the thread angle. So on an Acme thread, this angle here would be 2 alpha. So while the force F is pushing downwards, when we look at the normal component, we'll be looking at this angle here now is alpha. I'm looking at F divided by cosine alpha. We also looked at a case if we have a collar, supporting the load, and we said that an additional component of torque is needed to account for the friction between the collar and the load. So as we turn the screw, there is this additional friction that we need to resist. So assuming the load is concentrated at the mean collar diameter, we have this additional torque, TC, that is equal to the force multiplied by the friction coefficient between the collar and the load, multiplied by the diameter of the collar, DC, divided by 2. Today, we would like to start looking or analyzing the stresses that are developed in the power screw as we are raising a load. So if I look at a representation here of a thread, and I'm cutting here into the body of the power screw. So usually there is more than one thread engaged in the nut, but I'm using here a representation of one thread. And this power screw is supporting or is raising a force applied on the thread and the thread is wrapped around the power screw, and this load is exerting a force F. We are applying a torque T, whether to raise or to lower the load. And if I am raising the load, we found a TR. If I'm lowering, we found a TL. But the power screw supporting this load is always going to be in compression. And I'm going to be pushing here or putting a force on it, F. So I have here two internal forces, a normal force represented by F and a torque, because this torque is being resisting and supporting. So we have this internal torque. So as a result of these internal forces, so I have here a normal force that is equal to F, and I have a T that is going to be equal to the applied torque. The normal force is going to result in an axial stress. And this axial stress, sigma, is going to be equal to the force divided by the area. The area is going to be equal to pi multiplied by, when I'm looking at the body of the screw, I will be using the minor diameter. So there is a major diameter and a minor diameter. So here, if I'm looking at it, this is my major diameter D, and this here is my minor diameter dr. So I'll be using pi dr squared divided by 4, or I'm going to move the 4 up here. So I say 4f divided by pi dr squared. Now, if I consider my power screw in the XY plane, where Y is the vertical direction, then in the body of this screw, this axial stress is acting in which direction? This is my Y. This is my F, right? So sigma would be acting in the Y direction. So we can say we have a sigma Y that is equal to 4F divided by pi dr squared. As a result of the torque, I am also going to get torsional shear stresses. This torsional shear stress, tau, is equal to T divided by J multiplied by, if I want to find the maximum torque, I will multiply it by C, where C here, for C is equal to dr over 2, right? And J for a circular section is equal to pi dr squared divided by 32 for J. So when I apply here, I can find tau to be equal to C is dr over 2. And here I have dr squared. I'm sorry, this is dr to the power 4. Sorry for that. So I have 16t divided by pi dr cubed. If we're working in the xy plane, the torque, if I'm looking at the body, this is going to be, the torque is going to be applied perpendicular to the plane on the y face. So I really can think of this torque as acting in the, applied on the y face in the z direction. Next, we want to look at stresses in the threads of the power screw. So again, we are going to sketch we still have the force F applied on the threads. The thread has a minor diameter dr and a nominal diameter d. And as we look at the threads, the width of the thread is equal to the pitch over 2. And the width of the thread is also equal to P over 2. So we will be considering here the force applied halfway through. So this will be P over 4. And the distance also on this end would also be P over 4. As the force is exerted on the face of the thread, we do have bearing stresses. So I have a bearing stress, and this sigma uppercase B for bearing is a compressive stress that is equal to, I'm going to put a minus because it's compressive, the force divided by the area that is supporting the load. And this area is coming from P over 2 multiplied by the perimeter. And when we're finding the perimeter, we are going to be using the mean diameter, dm. So I will be looking here at the perimeter, pi dm, multiplied by the height, which is P over 2. But it is important to note that I do have more than one thread engaged. So I'm going to multiply this by the number, I'm going to call it NT, where NT is the number of engaged threads. As the force is applied on the thread is behaving like a cantilever beam. So it is fixed at one end, so we can think of this thread as a cantilever beam, and I have this force applied here. So if I calculate the bending moment, this is putting tension at the top and compression at the bottom, M. So this will be at the root, the tension would be at the root of the thread. So the bending axial stress at the root of the thread. This is due to a bending moment M, and this bending moment M is equal to the force multiplied by the distance, which is P over 4. So M is equal to the force multiplied by the moment arm, which is P over 4. The axial bending stress, as we learned, is sigma is equal to M divided by I multiplied by C. Of course, I can put a minus sign and then use a negative moment, or I can see here clearly that at the top of the root, it is a tensile stress. Now, I, the moment of inertia, is equal to, if I consider this like a rectangular area, but knowing that the width is equal to the perimeter. So my B, if I think of it as BH cubed over 12, B here is going to be equal to pi dr times the number of threads engaged, that's my B, multiplied by the height, which is P over 2, cubed, divided by 12. And C is the distance from the neutral axis to the root, and this is going to be equal to P over 4. So when I substitute in my equation, I will get a bending stress. So M is FP over 4. And then if I find C over I, we'll find that this will be equal to 24 pi dr nt times P squared. We can simplify that to sigma equal to 6F divided by pi dr nt times P. Now this bending stress is acting in which direction? Is pulling at the root of the thread in this direction. So this is, if this is XY, this sigma is acting on the X direction. Now, as I think of the behavior of a thread as of a beam, what other stresses are going to be there? So like I'm showing here a bending moment, there is also a shear force. This shear force, V equals to F, is going to lead to shear stresses that could lead to shear failure mode involving the stripping of the threads. Now, when I say the threads, these could either be of the nut or of the screws, right? Depending on which material is stronger. So when I say threads here, either of the nut or the screw. So how do we evaluate that shear stress? This shear stress tau, again, if we are thinking of the thread as having a rectangular section, the maximum shear stress for a beam that has a rectangular section is equal to 1.5 times the shear force divided by the area. And where does it act on a rectangular section? What is the maximum shear stress? If we have a rectangular section, the shear stress distribution is going to be parabolic like this, where I have a 0 at the bottom and the 0 at the top. And at the neutral axis of the section, I get this tau max that is equal to 3/2 V over A. So if I evaluate the shear force is equal to F, and the area is 2 pi dr multiplied by nt multiplied by the height, which is p/2. If I simplify that, I get 3f divided by pi dr nt times p. So these are the stresses that we calculated in the body of the power screw and in the threads of the power screw. I want to bring your attention to the root of the threads, because if you look at the roots here, wouldn't that be seeing the axial stress from the body of the screw? Yes. Would it also be seeing the torsional shear stress from the body of the screw? Yes. And it's also getting this axial stress in the x direction due to the bending of the thread itself. So we are looking at a stress at a point really combined stresses. So the best way to understand that is to look at a stress block and look at all the different effects so that we can evaluate whether failure is going to occur or not. So I want to combine the sigma y, this tau yz, and this bending stress that we called sigma x. So that's what I'm going to be doing next. We're going to consider a stress element at the root of the thread. But if I'm looking at my diagram here, I'll be looking at this point. So I have a root here and a root here. So we'll be looking at the top root of the thread. Basically the one that is in tension. Yep. Again, this is my x direction, y direction, and of course z would be out of the plane. So if I zoom on this point and imagine a stress element, this would be my x face, this is my y face, and this is my z face. And this is another good application for all what we've learned about stresses and stress elements. On the x face, I have the axial stresses from the bending of the threads. And we had here, we called it sigma x. And this sigma x was the bending stress that is equal to 6f divided by pi dr ntp. So 6f divided by pi dr nt times p. Right? Where dr is the minor diameter, and the height of the thread is p over 2. In the y direction, I have this stress that is compressive, as you can see, sigma y. And this is the axial stress in the body of the screw. So I have a sigma y that is equal to minus stresses in the body of the screw. We got the 4f divided by pi dr squared. And I really should put this as compressive, or I should put here a negative sign. So this sigma y is minus 4f divided by pi dr squared. And finally, we had the torsional shear stress acting on the y face in the z direction. So this is going like this. We had a tau y z. So I had a tau y z. And this is coming from the torsional shear stress. So it's equal to 16t divided by pi dr cubed. So knowing the load F and knowing the torque that is needed, we can calculate these three stresses. So what is the value of sigma z? Is there a sigma z? No. So I can come here and write a note that sigma z is equal to 0. And by the way, this is also true for tau xy is equal to tau xz is equal to 0. And of course, we know that shears always complement each other. So if there is a tau yz, there is a tau zy. Something to observe here, we have 0 shear stresses on the x face. If I have 0 shear stresses, then this sigma x must be a principal stress. So I'm looking here at a 3D stress element. Where tau x is equal to 0 on the x face. Therefore, sigma x is a principal stress. If I want to evaluate failure, I can use the ductile energy theory and evaluate my sigma prime. So we can obtain the von Mises stress using one of the equations in chapter 5, equation 514, where sigma prime is equal to 1 over the square root of 2 multiplied by sigma x minus sigma y squared plus sigma y minus sigma z squared plus sigma z minus sigma x squared plus 6 multiplied by tau x y squared plus tau y z squared plus tau zx squared, and you take the square root of all of this. This is equation 514. In the equation for sigma x, which comes from the bending of the thread, you will notice we have this NT, the number of threads engaged. And if we look at the thread deformation, in screw nut combination, we will find that the power screw thread is in compression. Which causing elastic shortening of the screw thread pitch. The engaging nut is in tension. This will cause elastic tensioning or lengthening of the nut thread pitch. As a result of that, or consequently, the engaged threads cannot share the load equally. So yes, there is more than one engaged thread, but they're not going to share the load equally. So experiments found that the first thread that is engaged carries actually the majority of the load, or 38% of the load. The second carries 25%. The third 18%. And by the time you get to the seventh thread, it is free of load. So it keeps decreasing until you get to the seventh thread is free of load. So what does that tell us? In our previous equations where I had this NT, it is not right to put the total number of threads because they do not share the load equally. But if I'm looking for the most critical stress, then I should be looking at the first thread engaged, which is handling or carrying 38% of the load. So if I want to find this largest stress, instead of dividing by NT, I can replace F by 0.38 F, right? So to find the largest stress in the first thread use 0.38 F in place of F and set NT to be equal to 1. Okay. Let's take an example. Is this concept clear to everyone about how I combined all the stresses on a stress element in 3D?